On October 4th, 1957, the Soviet Union launched Sputnik 1, the world's first satellite, into space. Scientifically, this launch was a tremendous event, as it not only successfully launched a man-made object beyond the Earth's atmosphere, but it also marked the beginning of a new technological age. Today, over 4,600 satellites are in orbit, all performing different functions that include communication, surveillance, and even scientific research. Whether it be watching television or navigating the Earth, satellite systems are crucial in our daily digital dependent lives. But to understand the effects of satellites, we must first ask ourselves, how do satellites work? Satellite signals are transferred in the forms of radio waves and microwaves. Both are a form of an electromagnetic wave. Other examples of electromagnetic waves include visible light, X-rays, and ultraviolet rays. Electromagnetic waves are vibrating electric and magnetic fields that carry energy in a specific direction. They can travel through a vacuum. Additionally, all electromagnetic waves are transverse. This means that as the wave travels, the messenger particle's vibrations are perpendicular to the direction of travel. This is opposed to a longitudinal wave, where the particle vibrates parallel to the direction of travel. A transverse wave can be classified by its frequency and wavelength. The frequency of a wave is the rate that it takes for a vibrating particle to complete one cycle of oscillation, or, in simpler terms, for the particle to return to its original location. Consequently, frequency is measured in hertz, or waves per second. Wavelength, on the other hand, is the distance from one crest, the highest point of a wave, to another crest, or from one trough, the lowest point of a wave, to another trough. Wavelength, as such, is measured in meters. It is critical to note that the frequency and wavelength of a wave are inverted. This means that a wave with a high frequency will have a short wavelength due to its rapid vibrations, while a wave with a low frequency will have a long wavelength. As such, all known electromagnetic waves have been ordered from highest to lowest frequencies on the electromagnetic spectrum. So why is it that we use low-frequency waves such as radio for transmission satellites? To answer that question, we must first understand the Earth's atmosphere. Over millions of years, the Earth's gravitational pull has prevented gases from floating off into space, instead retaining them around our planet and creating a blanket. As many already know, the Earth's atmosphere also consists of multiple layers. These layers of gas have helped absorb most of the high-frequency electromagnetic radiation, such as gamma rays and ultraviolet rays, that the sun emits. Without the atmosphere, multicellular life would never have developed due to the waves being deadly to most biological life. However, after millions of years of exposure to high-energy waves, the higher parts of the atmosphere, the thermosphere and mesosphere, have been ionized, or positively charged. This has created the ionosphere. Due to its positive charge, the ionosphere usually refracts high-frequency waves rather than allowing them to pass through to the exosphere, the outermost layer of the atmosphere where most satellites are located. Another factor is the rate of decay of an electromagnetic wave. As a wave travels, its intensity begins to grow weaker and weaker. High-frequency waves lose intensity much faster due to a higher rate of oscillation, meaning that the signal will be much weaker, while low-frequency waves can travel much further while retaining intensity, making them the preferable option for long-distance communication. Finally, low-frequency waves are capable of making a slight curve to adjust to the Earth's round shape, allowing them to travel in a slightly curved direction, which, in turn, also allows them to travel more distance around the Earth. In short, although more intense, waves with higher frequencies are better for short-range communication, while low-frequency waves are more suitable for satellite communication. So with that out of the way, how do we transmit a satellite signal? First, a signal starts in the uplink. This is the location on Earth that transmits the initial signal to a satellite. Then, the satellite receives the signal through a receiver. It processes this information, making any necessary adjustments such as amplification, and prepares to transmit the signal through a transmitter on a similar but new frequency. The frequency is slightly changed in order to be able to distinguish incoming signals from outgoing signals. Finally, a signal is received by the downlink back on Earth. Although there can be multiple downlinks, there can only be one uplink per signal. Also, although all satellites function in this manner, their orbit path, altitude, range of frequencies can all vary, meaning that each signal can be individual and unique. Now that you know how satellites work, look at the world around you. Television, cell phones, computers, the modern world practically functions on satellites. So the next time you flip on your TV or look up an address in Google Maps, think about the impact that satellites have had on your life.